This is LING 270, Language, Technology, and Society, Module 7, Intro to Language Technologies. In this lesson, we'll talk about the early developments and modern developments as well of speech synthesis. Mechanisms that have been developed to actually imitate human speech have been developed for hundreds of years. It's not just a new development that we've been able to imitate speech using computer technology. These machines are able to generate human sounds because they imitate the acoustic properties of human speech. So in this lesson, we'll be talking about how the human vocal tract works and how these machines imitate those acoustic properties. So in this lesson, we'll give an overview about the acoustics of the vocal tract. We'll describe the early developments that have been made in speech synthesis, so the inventions from hundreds of years ago, which attempted to imitate human speech. We'll also demonstrate the current state of the art in speech synthesis. So first of all, let's ask how speech sounds are produced. So some of this might be a review from LING 100 or LING 401 if you've taken that as well. So the way that our vocal tract actually produces a speech sound is first that a vibration is caused in the air. So that's a description of how a sound in general is produced. So when we're talking about the vocal tract, this vibration is caused by the vibration of our vocal folds in our trachea, and or it could be caused by whispering, where we simply breathe through our vocal tract. So these are two different ways of producing a vibration deep in our vocal tract, and that sound wave is modulated by the upper portion of the vocal tract. So the upper portion of the vocal tract contains your tongue, your lips, and your nasal cavity. And all of these aspects of our anatomy can be moved around. And as they're moved around, they change the acoustic filters of which are applied to the vibration, either from your vocal folds or from whispering speech. So it's the acoustic properties of these aspects of our anatomy which characterize the way we produce speech sounds. Early speech machines actually tried to mechanically replicate the organs of the vocal tract. So basically, they tried to make a machine which physically resembles the vocal tract in order to make human-like sounds. So that's how this kind of worked initially. So if we want to make a vowel sound with our vocal tract, for example, that sound can be changed by a few different factors, one of which is how high is our tongue in the mouth. So if our tongue is at a really high height, that makes container 1 here fairly long and container 2 very thin. And that changes the resonant properties of those areas of our vocal tract, and as a result change the result of the sound that we actually produce. And another aspect is how far to the front of our mouth or how far to the back that is our tongue located. So we can see that there's 2 dimensions of location where our tongue can move, and that results in the distribution of vowels that we're capable of producing. Additionally, we can change the sound of a vowel by rounding or unrounding our lips. Think of how you say a vowel oo and a vowel e. Those would be examples of how rounding your lips affects the acoustic properties of your vowel. And you can also change the sound of the vowel by opening a nasal cavity. So you can lower the velopharyngeal port and allow air to go through your nasal cavity, and that further changes the sound of a vowel. So typically, most commonly in our speech, we pronounce vowels by vibrating our vocal folds. But as I had mentioned in the previous slide, it's also possible to produce vowel sounds by whispering. So whispered vowels, they have the same, involve the same resonant properties of the upper vocal tract. They just involve a different kind of source. So they use a source of breath rather than the vibration of the vocal folds to produce these acoustic properties. So this leads us to talk about the idea of resonance. So these 2 containers here, the container 1 and container 2 correspond to the back of our throat, right behind our tongue, and container 2 corresponds to a container in our mouth. And both of these containers, because of their size and shape, they prefer to vibrate at a particular frequency. Of course, as we know from physics, that larger volumes of air will resonate at a lower frequency compared to smaller ones. And now what happens is that when we move our tongue around to change the size of these two containers, we produce different resonant frequencies that they will vibrate at, that as a result that filters the vibrations coming from our vocal tract in different ways. So that's why the resonant properties of our upper vocal tract is very important for the way that we can produce speech sound. If we actually look at how the vowels are produced according to their location of the tongue, we can actually plot them out on a two-dimensional diagram. So remember when I said that vowels can be pronounced with the tongue at the front or the back of the mouth, as well as high and or close to the roof of the mouth and low in the mouth. We can see that there are two spatial dimensions that your tongue can occur in, and a result two different dimensions of vowels that can be produced. So a lot of times linguists and phoneticians will plot vowels in this kind of two-dimensional distribution. And so we can see a diagram like this here. So, so the left side of this diagram corresponds to vowels which are front. The right side corresponds to back vowels. Vowels at the top of this diagram correspond to vowels where the tongue is high in the mouth, and the vowels at the bottom of the chart correspond to where the tongue is low in the mouth. These locations also correspond to the resonant frequencies of the trachea and the larynx as well. So, this is why this is one way we can characterize the acoustic properties of vowels. Now, when it comes to consonants, we have to describe them a little bit differently. So the word consonant itself actually comes from the Latin with sound, so which kind of tells us a lot about how consonants kind of work. So consonants are, generally speaking, they are formed by closing and releasing the airflow at some point in your mouth. And there are many different kinds of sounds like this, such as plosives. That would be a sound where you close the mouth all the way entirely and then release it to produce a consonantal sound. Some of which are caused by restricting the airflow at some point in your mouth, creating turbulence. Think of the F sound or the S sound. Those are examples of these kinds of sounds, and these sounds are called fricatives. So we can see that we can characterize consonants based on where this closure in the mouth occurs and how complete that closure is. If they're closed all the way, then we call that consonant a plosive. If it closes only partially and causes turbulence, then we call this sound a fricative. So as I mentioned when talking about vowels, the sound that we associate with the vowel is caused by the resonant frequencies of our upper vocal tract. And it's useful for phonetic analysis to actually plot what the resonant frequencies are while speech is being pronounced. So linguists do this by using what's called a spectrogram. So this plots a spectrum of the sound wave over time and lets you see how the resonant frequencies evolve over time. So this is a spectrogram of someone saying, "I can see you." It shows the various resonant frequencies how they evolve over time. So when we look at a diagram like this, we can see that vowels kind of look like caterpillars. Those correspond to areas of strong resonant frequencies. And as I mentioned with consonants, consonants correspond to a closure of the vocal tract. So that means there's not really any sound being produced in these areas, so they kind of look blank, but there might be a little bit of a release after that in the diagram. And fricatives look kind of like the thing we see near the letter S here. So the S kind of sounds like white noise. And when we look at that on a spectrogram, that corresponds to a broad range of frequencies all kind of being pronounced at the same time. So that's what a fricative can look like. And since consonants are speech sounds that kind of occur with another sound, a big way that we actually, so basically, a lot of times, since consonants are associated with the closure of the vocal tract, there isn't really a sound associated with them exactly. They're kind of more silent than anything else. But a big signature of the consonants is how they change the vowel that occurs around them. And we can see that the signatures of a B sound, for example, on the vowels that follow them look like the ones we see in this diagram below, and that differs from those that we see for a D sound and those which we see for a G sound. So, so in large part, we are able to hear a consonant based on how the vowels are affected nearby it. So, and this is important for the topic of speech synthesis. So a lot of systems that will attempt to synthesize human speech will involve playing the sound of a consonant and then a sound of a vowel separately. But what we can see in this diagram here is that it's actually really important to produce these two sounds together. So this was a development that only kind of came about in the recent development of speech synthesis. So one of the oldest developments of a mechanism which can actually imitate the sounds of human speech were Kratzenstein's vowel pipes. So these were a set of organ pipes which had a bunch of different shapes, and because they have different shapes, they have different properties of different kinds of resonant frequencies. So remember that our vocal tract has two resonating chamber in our mouth and a resonating chamber in our larynx in the back of our throat. And so these two, these areas produce two different resonant frequencies. And what Kratzenstein had done was he developed a set of pipes which actually have very similar resonant frequencies to this. So when you play an organ pipe through these pipes, you end up hearing a sound that sounds a lot like a spoken vowel. So here we can see an early awareness of the properties of vowels and how machines can be developed which actually imitate those sounds. And then another interesting invention, which would aim to be a more comprehensive imitation of human speech, is the Funklein Machine. And I've attached a video in this lecture series actually demonstrating how the Funklein Machine is used using a modern replica. Basically the way a Funklein Machine works is it tries to have a bunch of mechanical components which correspond to the organs of a vocal tract. It basically tries to make a mechanical replica exactly of the human vocal tract. So they use some reeds which vibrate against each other in the same way that vocal folds vibrate against each other. So that's the source, which is then filtered by the resonating chambers in the rest of the mechanism. It uses a set of bellows that kind of act like human lungs. The machine is actually operated by putting your hand inside the cavity in the box you see here. In that way, your hand is kind of acting like the tongue does in your mouth. So moving your hand around is the same as moving your tongue around in your mouth, and that changes the different kind of sounds that you can produce. And there are also some vents that occur on the top, which can make some kinds of hissing sounds, like you hear in fricatives, like sa and sha, for example. So in this way, this is a mechanism which can imitate a lot of the sounds that a human can actually produce. So what I'd like to invite you to do is to kind of listen to this machine and find out what kind of limitations this machine has. So we can see that it can generate a lot of human-like sounds, but is it really at a level which can make speech or even pronounce a single word for that matter? You'll see in the example that it's easy enough to produce a particular sound that a human can say, but producing a word or a sentence is something that's much more difficult. But nonetheless, this is a really interesting early development in speech synthesis. So after that, a few hundred years had passed before we see any major developments in speech synthesis. But by the time that a lot more had been developed in the way of electrical engineering, we see a new example of a speech synthesis system which actually was capable of generating very recognizable speech. And this was called the voice demonstrator, also known as voder. So voder is what we can consider the first electric speech synthesizer. It was developed by Bell Labs in 1939. Homer Dudley was the inventor. And it was it got a lot of notoriety by being demonstrated at the World Fairs in New York and San Francisco. And the way voder actually works is that it is a machine that kind of operates like an organ. There's a keyboard that corresponds to the different sounds that someone can produce. In particular, the left and right hand actually correspond to formant frequencies that are produced in your mouth and your larynx of your vocal tract. And there are some other components of the machine that change, for example, the tone of your voice and whether or not you're producing a fricative sound. So in this way, voder is very similar to the Funklein Machine. It has a bunch of components which correspond to sounds of the human vocal tract. But voder was really advanced in the sense that it could actually generate human recognizable speech. And I've attached this video in the lecture series as well, so you can actually listen to this demonstration of voder at the World Fair. And you'll see that voder is actually capable of saying very coherent sentences. And not only that, but also modifying the tone of its voice and even being able to sing a song. So this is kind of a really interesting development in speech synthesis. Now, nonetheless, there's still quite a lot of limitations for the voder system. The biggest of which being that it took several months to actually train someone to operate the voder. It required a lot of quick, complicated movements on the keyboard and the pitch pedal and the wrist bar, for example. So this was a very complicated skill that had to be developed. So this was not a very easily usable machine. So those were some limitations of the speech synthesizer. Now, modern speech technology, on the other hand, is much more developed and has come a much longer way since the voder has. We are currently at the point where speech synthesis systems are actually almost indistinguishable from a human voice. So think back to our analysis of artificial intelligence when we were talking about the Turing test, how that was used as a way of evaluating the quality of a technology by comparing it to a human. Here I have a link that you can go to if you are interested, where you can hear an AI system which actually makes a phone call to a restaurant and actually places a reservation. And at no point during the process does the person on the other side of the line suspect that this is some kind of unusual call, like a prank call or something. They respond to the AI system as if it is actually a person. And in large part, that's because of the very high quality of the voice system that has been developed. You can also try to find out yourself. One of which to do another example of a kind of Turing test for a speech technology system. So at this link here, you can listen to a recording of a human voice and a recording of a synthesized passage. They're both saying the same sentence, but one is a human and one is not a human. And they sound very, very similar to each other, and it's very difficult to actually tell the difference between them. And that kind of goes to show that speech technology has reached the point where it's almost indistinguishable from a human voice. So in this sense, speech technology has basically achieved parity with human quality. So to summarize what we talked about in this module, we've seen that there have been many mechanisms that have been developed over the years that imitate the properties of the human vocal tract, and as a result imitate the resonant frequencies or the formants of the vocal tract. So we looked at how Krassenstein's vowel pipes kind of imitated the resonance sounds of our of vowel sounds produced in a human vocal tract. And we've also seen how the Funklein machine can generate not only some vowel sounds using your hand acting like a tongue in the system, but also being able to produce fricative sounds, for example. We've looked at how the voter system was able to generate text that is very easily understandable, but was nonetheless fairly limited because of how difficult it was to operate. Now, since then, modern speech synthesis is at such a good quality that it's actually almost indistinguishable from human speech. And this just goes to show how far speech synthesis has come since its early developments.